They've already canceled the classes after 5 tonight, so. Luna, come, let's go this way a minute. Good, good girl. Let's go this way a minute.
I need a break. Yeah. I swear to God, if I'm sorry. I'm not really sorry. I'd be like, you get sick. I'm really sorry. Maybe I just think that I should take what? I'm not. So I always because I think that I was yeah, come here. Okay, folks. I was going to pass back quiz 1, but I would say about a third of the class is not here. You see on your online
everybody that turned it in got their 10 points. So I'm gonna save it for whenever most of the class is here. So that I can pass it back at that time. So just the announcements. Obviously, we're looking at a winter weather potential. And knowing it in advance helps me to explain the plan. I put it in writing last time because I didn't know in advance. So first of all, let me start with the third line. Basically, if the president says that UCA is open, then classes are meeting. If the president says we go online, then I'll go online. But I do need to mention the last piece, which is no matter what happens, as long as there is a potential for a snow event in this area, I'm going to give you a time frame. Minimum 2 hours before class, I will post something. Because, number one, last time I got more snow than Conway. I still didn't get much, but I got more snow than Conway. And so there was a chance that my house will get snowed in and Conway be clear as a bell. If that occurs, I can't come in. So I will have to Zoom one way or another. Unless, here's another issue, unless it's still snowing around my house, in which case I may not have internet because I have satellite internet. And therefore, classes will be canceled. So I can probably get a message out, but that's about it. So 2 hours, a minimum of 2 hours before class, I will post a message on Wednesday, letting you know what to expect.
So if we hear absolutely nothing, I'm going to assume you have no power.
Exactly. No, I can still use my cell phone. I can still get a message out. It's just, it's spotty where I live. So, let's hope there's power. Okay, so these are just notes in case we have inclement weather. If we do not have class on Wednesday, then the graphing lab, which is due at the start of class Wednesday, will get moved as to its due date. Or initially it'll get moved to Thursday morning or Thursday during lab. But if we have no lab on Thursday, then it's going to get bumped to Monday. So basically it's a play it by ear type of thing. The next time I see you, the lab is due. How is that? The next time I see you, the graphing lab is due. No matter what it is. The other thing I wanted to let you know is I looked at the calendar today and I realized exam number 6 is next Monday. I mean, exam number 1 is next Monday, February 6th. Hold on. And it will only cover whatever I have lectured about. So it does not necessarily cover everything. If you look at the syllabus, again, that was tentative what I was going to cover at any given time. It will only cover what I've lectured about.
Does that include the lecture videos, I assume?
That includes lecture videos, yes. Now, to help you, if you look at this week's Blackboard folder, you will see there's a new section which lists the materials for the lab that I expect to see on the exam as of right now. Obviously, that can change. You're going to have to be a little bit flexible. I've got to be a little bit flexible at this point.
So what do your exams look like?
They look like my optional homeworks to a large extent. Just as a reminder, you do have a quiz that's due at 11:59 p.m. tonight. That is quiz number 3. There are 5 questions because there's a lot of math. And homework number 3 is due on Sunday at 11:59. Again, that is always edited after Wednesday's lecture because it is directly dependent upon what I get as to what I can request of you. Any questions? Okay, so we're going to get into today's information. So on Wednesday of last week, we started talking about solution formation, and we looked at it from a quantitative standpoint to some degree. Basically, you have to add energy to break the solute, intermolecular force. You have to add energy to break the solvent, intermolecular force. And then when the solute and the solvent come back together, they give off energy when they have that attraction, that intermolecular force. Now, whether a reaction is going to be endothermic or exothermic in solution formation is directly related to those two energy differences. If you have to put a lot more energy in to break the solute and the solvent bond, then is generated in making the solvent intermolecular force, then it's going to be endothermic. However, if you give off more energy in making the solvent intermolecular bond than it took to break apart the solute and the solvent, then it is going to be exothermic. Exothermic reactions typically will occur. I would say 99% of the time an exothermic reaction will occur. It's really if those intermolecular forces or the energy required to break the solute and the solvent are roughly equivalent to the formation of the solute-solvent interaction, that we're at a cusp of, is it going to occur? Is it not going to occur? Is it going to be exothermic? Is it going to be endothermic? Because they're pretty much equal. From a quantitative standpoint, at this juncture, that's all we're really going to discuss with respect to solution formation. What I want to focus on today is the qualitative aspects, and then we're going to talk about some factors that impact the solubility, and also get into concentration units. Because if all goes well, we will be dealing with concentration conversions on Wednesday. Now, before I get into this, I did want to make one new note, and that is there is a type of intermolecular force that we haven't talked about yet. That is present in many of the solutions we deal with. And that is going to be a ion dipole force. So in other words, it's an attraction between an ion to a polar molecule. This is the type of intermolecular force that comes when you have an ionic compound dissolve in water. You will have an ion dipole intermolecular force. So I wanted to wait until this point to bring this particular one up because it is relative to solution formation. And it is an extremely strong force. Okay, so now what we're going to do specifically is we are going to get into qualitative solution formation. And to do so, you need to remember the term like dissolves like. And what we mean by like dissolves like is polar is going to react with polar, non-polar wants non-polar.
We call a solution soluble if the solute dissolves into the solvent, but we also will use the term miscible if we're talking about the solute and solvent both being liquids. So miscible and soluble are really the same thing. It's just the state of matter of the solute and solvent. If the solid does not dissolve in solution or in the solvent, then that is considered to be insoluble. Or if we are talking about a liquid solute and a liquid solvent, then we use the terms immiscible. So to move to some examples. We are going to look at water. And what I'm writing at the top is going to be the solvent. We're going to look at possible solvents of water. Let's look at CCl4, which is tetrachloromethane. Let's talk about methyl ether, which is CH3OCH3. And let's talk about methanol. And what we're going to do is what solvent will the solute make a solution with? That is the question we're going to answer. Now, to help us in answering this, the first thing I would recommend is identifying the intermolecular force in each of these. And when I talk about the intermolecular force, we're going to talk about the strongest of the forces. So with water, we have hydrogen bonding. With tetrachloromethane, it is going to be London dispersion because it is a nonpolar molecule. With our methyl ether, it is going to be dipole-dipole because that oxygen will have a lone pair and it will make it into a bent-shaped molecule. And then the methanol, because it is a small CH3 group attached to an OH, this is also going to have hydrogen bonding. Now, our possible solutes. Let's talk sodium chloride. Where would we expect the sodium chloride? Which substances would we expect the sodium chloride to go into? It's going to go into polar molecules. So which are they? It is going to go into everything except the carbon tet. Now, here's one of the things you need to understand. This is an ionic compound, which means you have a permanent cation and anion. And so it's actually going to prefer substance with the strongest dipole. So who would have the strongest dipole? Water. So this is going to be a preference. What else? Your methanol also has hydrogen bonding, so it's going to like it pretty well as also. And then you will have some sodium chloride dissolve in the methyl ether. It won't be near as strong. So what I'm trying to point out with this is if you have a permanent plus and a permanent negative, it wants a permanent plus and a permanent negative, which means it needs a dipole. But because this is a positive separate from a negative, it's going to prefer something that has the strongest dipole. Okay, let's look at the next one. Let's look at iodine. What would be the best solvent for iodine? It would be carbon tet. The reason is because iodine is a non-polar molecule. So it wants a non-polar solvent. Let's look at ethanol, which ethanol is CH3, CH2OH. So looking at the list of possible solvents, what would we expect for ethanol? It's CH3, CH2OH. Something with a hydrogen bond. Or at very minimum, you want a polar dipole-dipole. So it's going to be just like our sodium chloride, where it's preferable to go into the two with hydrogen bonding, since it hydrogen bonds, but it's acceptable to go into the methyl ether or dimethyl ether. Okay, our next one is benzene. Benzene is C6H6. You have the list of solvents. Because it is nothing but carbon and hydrogen, it's nonpolar. And so the only nonpolar option, which is carbon tetrachloride. What about toluene? Toluene is C7H8. Same thing, because it is still a nonpolar and it wants a nonpolar. Folks, if I use words like benzene or toluene or ethanol, I'll make sure to give you the formula too. I'm not expecting you necessarily to know the formulas, because technically benzene and toluene are things you would learn in organic. So, okay, so you get the gist though. Like dissolves like. Basically, if you've got a polar molecule, it wants a polar solvent. If it's got a strong if it's highly polar, meaning it hydrogen bonds or is ionic, then it wants a solvent that can hydrogen bond. That's its preference. Okay. So now we're going to talk about what can affect solubility. We talked about like dissolves like, but but when we start thinking, for instance, about an ionic compound, sodium chloride pretty much goes into water and you can put a ton of it in there without it falling out of solution. But there are some compounds that you can only put a small amount in there before they start falling out of solution. So what we're going to do is we're going to look at what affects the solubility of ionic compounds. And CPDS means compounds in my world. Now for this, the big thing you're going to need to be able to do is you're going to need to be able to interpret a solubility curve. So here is a common solubility curve. And what I want to do is take a photo so I can write on it. Okay. Now, first thing you will note is that for the majority, as you increase the temperature, because the temperature is on the x-axis, you increase the solubility because that is on the y-axis. Now, there are exceptions to that rule, such as it's like my pen is not wanting to be nice to me again. Such as this cerium sulfate. This would be an exception to the rule, is the cerium sulfate. But the majority, they actually prefer to be the temperature increase, your solubility increases. Now, another thing I want you to note is the unit. It is the grams of that salt per 100 grams of water. So now I'm going to ask some questions. I can't write them down because I can't keep up the screen and write, but I will do my best to walk you through it. So the first question, according to this graph, which substance maintains an almost constant solubility over the temperature range given, which is 0 to 100 degrees Celsius. Sodium chloride. Sodium chloride is the only one that pretty much, I mean, we started at about a 34 and we made it up to about a 40 gram per 100 gram. We've already mentioned this one. Which substance does not follow the typical trend with respect to temperature and solubility? The cerium sulfate, because the cerium sulfate solubility decreases with an increase in temperature, which is the reverse of what is normal. Okay, the third question. What is the solubility of KClO3 at 20 degrees Celsius? KClO3 is this line here. And we're looking at about 20 degrees Celsius. 7, 8, somewhere in there. And yes, folks, I do give you a range. It's not exact. Now, before I can ask the next question, I need to explain another concept. So these are at a given temperature. At a specific given temperature, if the mass of the solute is on the line, that is considered to be a saturated solution. If the mass of the solute at a given temperature falls on the line, it is considered to be a saturated solution. If the mass is above the line, then it is a supersaturated solution. I will in just a moment. We'll play with one of them and I'll show you. And then if it is below the line, it is considered to be unsaturated. And folks, what these terms mean. An unsaturated solution means you can add more solute and it'll still dissolve. A saturated solution is right at that specific point that if you were to add more solute, it's just going to fall right out. And a supersaturated solution means there's actually more solute there than should be. And usually to make supersaturated solutions, we have to do something like heat the water up to a specific temperature, dump in our solid, and then leave it and not touch it. Because any type of outside influence will cause it to crash right back out. So now, I was asked to explain in further detail what all of this meant. So I'm going to take this KClO3 line because there's a decent distance right about here. If I were to say at 60 degrees, and I put in 10 grams of KClO3 for 100 grams of water, because it is below the KClO3 line, that means it's unsaturated. But if at 60 degrees, I were to put in 37 grams, where it lands on the line, now it's saturated. And then if I were to say at 60 degrees and 40 grams, because it's above the line, it's supersaturated. So now with that in mind, we have a solution that contains 50 grams of calcium chloride. And it's at 10 degrees. So we go up 10 degrees and 50, and we see where that follows with calcium chloride. Since it's below the calcium chloride line, it's unsaturated. Okay, now this one is, I'm gonna actually try to draw this, even though it's hard to do on these graphs. Let's see if I can grow this thing some, maybe. Let me, nope. Okay. So this next question says, first of all, we're dealing with KCl. So you're looking at this line. I'm trying to go over with my marker or my pen. And hopefully it looks darker now. You're looking at that particular line. This question says, a supersaturated solution at 10 degrees contains 40 grams of KCl. So we are at 10 degrees and 40 grams. So we're right here above the letters NaCl. At what temperature was the solution saturated before being cooled to 10 degrees? So this thing got cooled to 10 degrees. So if we're going to have 40 grams and it be saturated, it's going to be right around the 40-degree mark. So we heated this up to 40 degrees, which allowed us to add 40 grams of potassium chloride into 100 grams of water. We heated it up to 40 degrees to get that 40 grams in to that 100 grams of water. We then cooled it to 10 degrees. So we went from a saturated solution at 40 down to a supersaturated solution when it was at 10. Now, the next one says, okay, we're going to start with this supersaturated solution at 10. And we have kept it undisturbed, but all of a sudden we disturb it. As soon as you disturb a supersaturated solution, anything that's in excess is going to precipitate out. So how many grams precipitates out? Anything in excess precipitates out. So what it means is 10 grams is going to precipitate out because that was what was in excess of the saturated solution. Now I have one more. $25 grams of potassium nitrate, 25 grams of potassium nitrate at 30 degrees Celsius is dissolved, well, that's not correct. 25 grams of potassium nitrate at 30 degrees Celsius is dissolved in 50 grams of water. Is the solution saturated, supersaturated, or unsaturated? 25 in 50 of potassium nitrate. So one more time. If I add 25 grams of potassium nitrate, for those that have trouble seeing the line, the potassium nitrate is this green line. If I have 25 grams of potassium nitrate in 50 grams of water, is it saturated, supersaturated, or unsaturated?
At what temperature?
30. Okay, I got all of them. How many thinks it is unsaturated? How many thinks it is saturated? How many thinks it's supersaturated? Okay, the key to this is you had to pay attention to the units. 25 grams in 50. This is in 100 on this graph, so you had to double it. So you had to find 50 grams of potassium nitrate at 30. And so I would have said it was probably saturated, but I would have given those that said super saturated a little bit of a wiggle room because it's close. It's very close. It's all about if you just touch this way or touch that way.
So then how does what you're talking about doubling it, how does that?
We just did because I said there was 25 in 50.
Oh.
But if you're going out of 100, that means it's 50 out of 100.
Okay, I see.
So you have to pay attention to that unit or you will mess up. You can expect a set of these questions on the test. Now, I want to look at the next piece. And the next piece, we're going to make it easy. Because you're not going to have to read a graph. You just got to know the concept. So we talked about dissolving a solid in water in that particular case. And basically we said, as a trend, you increase the amount of solute that can go into solution as you increase the temperature. There's oddballs. There's always going to be exceptions to the rule, but as a trend. Now what we're going to do is look at gases. And folks, you actually have, well, you may or may not have some experience with this. So let's just talk about pressure to begin with. How many of you have ever had a soda? How did they get the carbonation in? They put it under pressure. So what happens is you start with I gotta do that again. You start with a gas that is above the liquid line, as is in the example on the left. Now, when you add pressure, to this, what you're doing is you're forcing all of those gas molecules to come into closer vicinity than they originally were. And because they're in closer vicinity of the liquid, some of those gas molecules are going to lose energy as they collide with the surface, and they are going to be forced into the liquid. Now, a term we haven't really discussed much is dynamic equilibrium. There is an equilibrium, as long as you're at a constant temperature, there is an equilibrium about the amount of gas that is above the liquid level and the amount of gas that is below the liquid level. When you disturb a system that is at equilibrium, it's going to adjust accordingly. So in this case, when we added this pressure on that, in this case, that to this gas, and we caused a smaller area above the liquid level, what that means is it forced additional particles to go into solution. So what you can say is if you increase the pressure, you're going to increase the gas that dissolves in solution. That's what it comes down to. Increase pressure, increase gas in solution. Now, before I even just show the next thing, let's talk about temperature. Has anybody ever left a closed full can of Coke outside in their vehicle when it was 100-degree day, and so it's probably 130, 140 in your vehicle? I got at least one head. What happened to it?
It's on the roof of my, it's on the ceiling of my truck right now. It exploded.
It explodes. So before I show you the picture, what would you say is the solubility of gas related to temperature? Huh?
Decreased temperature, decreased gas. So it decreases solubility because it's going out of the liquid.
Well, she said decreased temperature. So you are both correct. It is as you increase the temperature of a solution that contains a gas, you will decrease the amount of gas that goes into solution. As you increase the temperature of a solution that contains a gas solute, you decrease the amount of gas in solution. And it will explode and make a huge mess. Temperature, and the y-axis is the solubility of gas in terms of molarity. Questions? Okay, so basically what is going on is you have gas in your liquid. As you increase the temperature, you're providing that liquid with more and more energy. As you provide the liquid with more and more energy, these gas molecules go crazy. And as the gas molecules go crazy, they're not going to like it and they're going to escape. And that is our short break. So we have a 2-minute break. Oh my. Yes.
So I was trying to do the homework last night and I was getting very frustrated. So right here, I understand how you got this number.
Mhm.
I do not understand how it went to this number.
Okay, so this is multiplication.
Mhm.
Right here, between here and here is multiplication. So you might as well have a my pencil won't work. So to get rid of multiplication, what do?
Divide.
So you should have taken that number divided by that number.
Okay. I feel like I did that, but it gave me a really weird number. But
Let me see, maybe I'm not infallible.
oh, I don't think it was anything.
Oh,
wrong with
well,
your-
it could be. It could be. Don't give me too much credit. So, 0.12320,656 comes out to be, here we go.
So why didn't you use? Oh wait, you did that. I'm so confused then. Okay.
No, it's negative because I didn't put the negative in because it was too much, but
Yeah, no, you're fine. I have no clue. I was so frustrated because I was trying everything I knew. Because you know what? I feel like I still maybe I multiplied this or yeah, multiplied everything
Okay.
by this.
I left that for last because of that. It's attached to that negative bill page of paper.
Okay, okay.
So I wanted to leave it for last, just like 1/x, that particular
Yes.
piece I left to last because, and then I always take the inverse at the last minute.
Okay, that makes sense.
So if it's attached to it, I kind of try to leave it for last and manipulate everything else.
I was sitting here thinking, I know how to do algebra. I don't know what I'm doing wrong though. I was so frustrated. But you know what? We got it. You know, no, it's division. I will keep that in mind because that was such a simple fix. And I'm like, this is making me so bad. All right. Thank you so much.
Not a problem. Okay. 2 minutes does not last long. Okay, folks. So what we're going to do now is I'm going to introduce the units of concentration. We're going to do some calculations that are hopefully straightforward with units of concentration so that if we meet on Wednesday, we can start doing conversions between concentration units. Now, there are a variety of concentration units that can be used. Some of which you may have seen, well, one of which I know you saw last semester, and that is molarity is equal to mole solute over liters of solution. That is still our primary go-to, but there are a huge variety of concentration units, some of which you probably encounter on a relatively frequent basis, and some of which you may have never seen. Another set of concentration units is going to be our percent concentration units. When we deal with percent concentration units, there are 3 different types, and so it has to be stated. There is the mass to mass percent, or sometimes referred to as the percent by mass. And that is going to be grams of solute over grams of solution times 100. Another one is the volume to volume percent, which is used anytime your solute and solvent are both liquids. Or in other words, the percent by volume. And that is going to be milliliters of solute over milliliters of solution times 100. And the last one is a mass volume percent. Which is going to be grams of solute over milliliters of solution times 100. A lot of times you'll see these used when you go to and purchase, for instance, 3% peroxide, 70% isopropyl alcohol, or if you're looking at percentages on labels, they like to use these types of percentages. Now, if you're talking about water contamination or air contamination, you might hear some other terms like parts per million or ppm. Which is mass of solute over mass of solution times 10 to the 6. So in other words, it's a lot like the percentages. Looks just like the percentages. Except the multiplier. There is also parts per billion. And again, that's going to be in ppbs, which is mass of solute over mass of solution times 10 to the 9th. And finally, more recently, we have been able to go into the parts per trillion. Which, as you hopefully would guess at this trend, is going to be the mass of solute over the mass of solution times 10 to the 12th. Now, depending upon gas law, and who you had, and perhaps in other locations as well, you might have heard of a mole fraction, which is also a unit of concentration. A mole fraction is represented by the letter chi. And you can do the mole fraction for everything in a solution. So we can do it for the solute, which would be the moles of solute divided by the moles of solution. Or we can do it for the solvent, which is going to be the moles of solvent over mole of solution. Now, folks, mole fractions are going to be particularly important when we get into dealing with vapor pressures of solutions. You'll be using them. Now, what do you notice every single one of these have in common so far? Well, they're all division. Huh? Something of solution is always at the bottom. So you notice that solution's always the bottom. Now, there is one oddball unit of concentration, and that is molality, which is represented by typically a italicized M, lowercase, to separate it from molarity, which is a capital M. And molality, folks, is a lot like molarity, except for the denominator. Molality is mole solute over kilograms of solvent. Molality, actually, the reason we use molality is not temperature dependent. All the rest of them are temperature dependent. Oh, now, folks, if I were you, I would probably take and get a 3x5 or 5x7 card and write all of these on it, so that when you're working through the next batch of problems, it'll be a little bit easier. Because when you're trying to calculate the molarity or the molality or the mole fraction, what you got to keep in mind is, what is in my numerator? What is in my denominator? And so until you get very comfortable with all of these, it might be nice to have a little card that you can just sit there with everything, and so you can refer back and forth. And yes, when you have to do solution calculations, I won't give you molarity. I'll give you all the rest. You never get molarity again. Because if you don't know it by now, you need to go back to College Chem 1. There's a few things I'll say that about. Not a lot, but this is one of them. Okay, so let's look at an example. 6.80 grams of NaCl are added to 2,750 milliliters of water. Find the mole fraction of sodium chloride. Mole fraction of sodium chloride will be equal to the moles of sodium chloride over the moles of solution. Where the moles of solution is equal to the mole of solute plus the mole of solvent. So in other words, we need to convert all of this into moles. The other thing that you're going to need to know for this is that the density of water, unless stated otherwise, assume is 1.00 gram per milliliter. Okay, step number 1. I'm going to figure out the moles of my NaCl. So I was told in the problem I had 6.80 grams of NaCl, and I want to convert that into moles of NaCl. That means I'm going to need the molar mass of NaCl. 6.80 grams of NaCl is where I'm going to begin. The molar mass of NaCl is 58.45. So I'm going to divide by the 58.45 grams of NaCl to 1 mole. Which that comes out to be 0.116 moles of NaCl. Now I'm going to work at the mole of solution, moles of solution. But I'm going to have to, I've already got the moles of solute to solve for that, but now I need the moles of solvent. We were told in the problem we had 2,750 milliliters of water. Water has a density of 1.00 grams of water to 1 milliliter of water. And then we can use the molar mass of water, which is 18.01 grams of water, is 1 mole of water, in order to get our solvent into moles. And that comes out to be 152.8 moles of water. Now we can get our moles of solution, which is going to equal to 0.116 moles of NaCl plus the 152.8 moles of water. And so we get a moles of solution equal to 152.916. Now you have the 2 components to solve the mole fraction. So the mole fraction for our NaCl is going to equal the moles of NaCl, which was 0.116 moles, divided by the moles of solution, which is 152.916 moles. And when you key that out, you get a value of 7.59 times 10 to the negative 4. Mole fractions do not have units. Now, if I had have asked, okay, so what is the mole fraction of the water for this? There are two ways to go about that. The first way is, yes, you could calculate the mole fraction of the water as the moles of the water over the moles of solution. But the easier way is to understand that the mole fraction of a solution equals 1. So the easiest way would say, okay, 1, so the mole fraction of a solution is equal to the moles of the solute, or the mole fraction of the solute plus the mole fraction of the solution. So 1 is equal to 7.959 times 10 to the minus 4 plus the mole fraction of our, not solution, that should have been solvent. And you would have gotten the mole fraction of your water equal to essentially 0.999. Technically, if we went past 3 decimal points or 3 significant figures, we would get into a more accurate reflection in this case. But questions about that? Don't worry, there's going to be more practice. Okay, let's look at another example. Yes. I'm going to give you everything but molarity. So no. Exactly. How many grams of magnesium cyanide would you need to add to 275 milliliters of water to make a 0.075 molal solution? First thing I note, folks, is anytime I see molality, it is mole solute over kilograms of solvent. So if I have a 0.075 molal solution means I have 0.075 moles of solute, in this case would be magnesium cyanide, in 1 kilogram of water. Folks, anytime you have something that is a fraction, to me, that screams, ugh, a conversion factor. So in this particular case, the molality is going to be a conversion factor. So we're going to take the 275 milliliters of water to be able to use this, to use the molality, we need to convert that into grams of water. And there is, again, that's always, we're going to rely on the density of 1.00 grams of water to 1 milliliter of water. Now you can use your, and you've got to pay attention to your units, folks. You got to pay attention to units. We're in grams, so we need that to be in kilograms. So we have 1,000 grams of water is 1 kilogram of water. And we had to do that in order to use our molality to convert that into moles of magnesium cyanide. I'm going to stop there momentarily and finish the calculation. Which comes out to be 0.02063 moles of magnesium cyanide, but always make sure you answer the question at hand, which asked you for grams. And the molar mass of magnesium cyanide is 76.3 grams to 1 mole. So that comes out to be 1.6 grams of your magnesium cyanide that you must add to 275 milliliters of water to get a 0.075 molal solution. Again, that number says 1.6 grams of magnesium cyanide had to be added to 275 milliliters of water to make a 0.075 molal solution. We will pick up with more of these math problems on hopefully Wednesday, but maybe via Zoom, who knows? Just keep your ear open. This is, by the way, none of the concentration stuff is on the test. I will save that for the next exam. Thank you.
You're welcome.